Welcome to Lesson 2, where we're going to be taking a deeper dive into computer vision applications and taking some of the amazing stuff that you've all been doing during the week and going even further. So let's take a look. Before we do, a reminder that we have these two really important topics on the forums. They're pinned at the top of the forum category. One is fact resources and official course updates. This is where if there's something useful for you to know during the course, we will post there. Nobody else can reply to that thread. So if you set that thread to watching and to notifications, you're not going to be bugged by anybody else except stuff that we think you need to know for the course. And it's got all the official information about how to get set up on each platform. Please note, a lot of people post all kinds of other tidbits about how they've set up things on previous solutions or previous courses or other places. I don't recommend you use those because these are the ones that we're testing every day and that the folks involved in these platforms are testing every day, and they definitely work. Okay, so I would strongly suggest you follow those tips. And if you do have a question about using one of these platforms, please use these discussions, not some other topic that you create, because this way people that are involved in these platforms will be able to see it and things won't get messy. And then secondly, for every lesson there will be an official updates thread for that lesson. So lesson 1 official updates, and the same thing, only Fast AI people will be posting to that. So you can watch it safely, and we'll have all the things like the videos, the notebooks, and so forth. And they're all wiki threads, so you can help us to make them better as well. So I mentioned the idea of watching a thread. So this is a really good idea, is that you can go to a thread, like particularly those official update ones, and click at the bottom, watching. Okay, and if you do that, that's going to enable notifications for any updates to that thread. Particularly if you go into, click on your little username in the top right, preferences, and turn this on, that'll give you an email as well. Okay, so any of you that have missed some of the updates so far, go back and have a look through, because we're really trying to make sure that we keep you updated with anything that we think is important. One thing which can be more than a little overwhelming is even now, after just 1 week, the most popular thread has 1.1 thousand replies. So that's an intimidatingly large number. I've actually read every single one of them, and I know Rachel has, and I know Sylvain has, and I think Francisco has. But you shouldn't need to. What you should do is click Summarize this topic, and it'll appear like this, which is all of the most liked ones will appear, and then there'll be View 31 hidden replies or whatever in between. So that's how you navigate these giant topics. That's also why it's important you click the like button, because that's the thing that's going to cause people to see it in this recommended view. So when you come back to work, hopefully you've realized by now that on the official course website, course-v3.fast.ai, you will click Returning to Work, you will click the name of the platform you're using, and you will then follow the 2 steps. Step 1 will be how to make sure that you've got the latest notebooks, and step 2 will be how to make sure you've got the latest Python library software. Okay? They all look pretty much like this, but they're slightly different from platform to platform, so please don't use some different set of commands you read somewhere else. Only use the commands that you read about here, and that will make everything very smooth. If things aren't working for you, if you get into some kind of messy situation, which we all do, just delete your instance and start again. Unless you've got mission critical stuff there, it's the easiest way just to get out of a sticky situation. And if you follow the instructions here, you really should find it works fine. So this is what I really wanted to talk about most of all, is what people have been doing this week. If you've noticed, and a lot of you have, there's been 167 people sharing their work. And this is really cool because it's pretty intimidating to put yourself out there and say, like, I'm new to all this, but here's what I've done. And so examples of things I thought was really interesting was figuring out who's talking. Is it Ben Affleck or Joe Rogan? I thought this was really interesting. This is like actually very practical. I wanted to clean up my WhatsApp downloaded images to get rid of memes. So I actually built a little neural network. I mean, how cool is that to say like, oh yeah, I've got something that cleans up my WhatsApp. It's a deep learning application I wrote last week. Why not? Like, it's so easy now. You can do stuff like this. And then there's been some really interesting projects. One was looking at the sounds data that was used in this paper. And in this paper, they were trying to figure out what kind of sound things were. And they got, as you would expect, since they published a paper, they got a state-of-the-art of nearly 80% accuracy. Ethan Sutton then tried using the lesson 1 techniques and got 80.5% accuracy. So I think this is pretty awesome. Best as we know, it's a new state-of-the-art for this problem. Maybe somebody since then has published something. We haven't found it yet. They take all of these with a slight grain of salt, but I've mentioned them on Twitter, and lots of people on Twitter follow me, so if everybody knew that there was a much better approach, I'm sure somebody would have said so. This one is pretty cool. Suvash has a new state-of-the-art accuracy for Devanagari text recognition. I think he's got it even higher than this now. And this is actually confirmed by the person on Twitter who created the data set. I don't think he had any idea. He just posted, hey, here's a nice thing I did. And this guy on Twitter was like, oh, I made that data set. Congratulations, you've got a new record. So that was pretty cool. I really like this post from Alina Harley. She describes in quite a bit of detail about the issue of them metastasizing cancers and the use of point mutations and why that's a challenging, important problem. And she's got some nice pictures describing like what she wants to do with this and like how she can go about turning this into pictures. Hey, see, this is the cool trick, right? It's the same with this sounds one, turning sounds into pictures and then using the lesson 1 approach. And here it's turning point mutations into pictures and then using the lesson 1 approach. And what did she find? It seems that she's got a new state-of-the-art result by more than 30%, beating the previous best. Somebody on Twitter who's a VP at a genomics analysis company looked at this as well and thought it looked to be a state-of-the-art in this particular point mutation one as well. So that's pretty exciting. So you can see, when we talked about last week, this idea that this simple process is something which can take you a long way. It really can. I will mention that, something like this one in particular is using a lot of domain expertise. Like it's figuring out what picture to create. I wouldn't know how to do that because I don't even really know what a point mutation is, let alone how to create, something that visually is meaningful that a CNN could recognize. But the actual deep learning side is actually pretty straightforward. Another very cool result from Simon Willison and Natalie Down. They created a Cougar or Not web application over the weekend and won the Science Hack Day award in San Francisco. And so I think that's pretty fantastic. So lots of examples of people doing really interesting work. Hopefully this will be inspiring to you to think, wow, this is cool that I can do this with what I've learned. It can also be intimidating to think like, wow, these people are doing amazing things. But it's important to realize out of the thousands of people doing this course, I'm just picking out the kind of a few of the really amazing ones. And in fact, Simon is one of these very annoying people like Christine Payne, who we talked about last week, who seems to be good at everything he does. He created Django, one of the world's most popular web frameworks. He founded a very successful startup and blah, 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 blah. So, one of these really annoying people who tends to keep being good at things. Now it turns out he's good at deep learning as well. So, that's fine. Simon can go and win a hackathon on his first week of playing with deep learning. Maybe it'll take you 2 weeks to win your first hackathon. That's okay. And I think it's important to mention this because there was this really inspiring blog post this week from James Dellinger, who talked about how he created a bird classifier using the techniques from lesson 1. But what I really found interesting was at the end, he said he nearly didn't start on deep learning at all because he went to the scikit-learn website, which is one of the most important libraries of Python, and he saw this. And he describes in this blog post about how he was just like, that's not something I can do, that's not something I understand. And then this kind of realization of like, oh, I can do useful things without reading the Greek. So I thought that was a really cool message. And I really want to highlight, actually, Daniel Armstrong on the forum, I think really is a great role model here, which was he was saying, I want to contribute to the library. And I looked at the docs, and I just found it overwhelming. And his next message one day later was, I don't know what any of this is. I didn't know how much there was to it. It caught me off guard. My brain shut down. But I love the way it forces me to learn so much. And then, one day later, I just submitted my first pull request. So I think that's awesome, right? It's this kind of, like, it's okay to feel intimidated. There's a lot, right? But just pick one piece and dig into it. You know, try and push a piece of code or a documentation update or create a classifier or whatever. So here's lots of cool classifiers people have built. It's been really, really inspiring. Trinidad and Tobago Islander versus Masquerader classifier, a zucchini versus cucumber classifier. This one was really nice. This was taking the dog and cat breeds thing from last week and actually doing some exploratory work to see what the main features were, and discovered that they could now create a hairiness and classifier. And so here we now have the most hairy dogs and the most bald cats. So there are, interesting things you can do with interpretation. Somebody else on the forum took that and did the same thing for anime to find that they had accidentally discovered an anime hair color classifier. We can now detect the new versus the old Panamanian buses correctly. Apparently these are the new ones. I much prefer the old ones, but maybe that's just me. This was really interesting. Henry Palachi discovered that he can recognize with 85% accuracy which of 110 countries a satellite image is of, which is definitely got to be beyond human performance of just about anybody. Like, I can't imagine anybody who can do that in practice. So that was fascinating. Batik cloth classification with 100% accuracy. Dave Lawar did this interesting one. He actually went a little bit further using some techniques we'll be discussing in the next couple of courses to build something that can recognize complete or incomplete or foundation buildings and actually plot them on aerial satellite view. So lots and lots of fascinating projects. So don't worry, it's only been 1 week. It doesn't mean everybody has to have had a project out yet. A lot of the folks who already have a project out have done a previous course, so they've got a bit of a head start. But we'll see today how you can definitely create your own classifier this week. So from today, after we dig a bit deeper into really how to make these computer vision classifiers in particular work well, we're then going to look at the same thing for text. We're then going to look at the same thing for tabular data, so kind of more like spreadsheets and databases. Then we're going to look at collaborative filtering, so kind of recommendation systems. That's going to take us into a topic called embeddings, which is basically a key underlying platform behind these applications. That will take us back into more computer vision and then back into more NLP. So the idea here is that it turns out that it's much better for learning if you kind of see things multiple times. So rather than being like, okay, that's computer vision, you won't see it again for the rest of the course, we're actually going to come back to the two key applications, NLP and computer vision, a few weeks apart. And that's going to force your brain to realize, like, oh, I have to remember this. It's not just something I can throw away. So we are... for people who have more of a hard sciences kind of background in particular, a lot of folks find this, hey, here's some code, type it in, start running it approach, rather than here's lots of theory approach, confusing and surprising and odd at first. And so for those of you, I just wanted to remind you, this basic tip, which is keep going. You're not expected to remember everything yet. You're not expected to understand everything yet. You're not expected to know why everything works yet. You just want to be in a situation where you can enter the code and you can run it and you can get something happening, and then you can start to experiment and you kind of get a feel for what's going on. And then push on. right? Most of the people who have done the course and have gone on to be really successful watch the videos at least 3 times. So they kind of go through the whole lot and then go through it slowly the second time, and then they go through it really slowly the third time. And I consistently hear them say, I get a lot more out of it each time I go through. So don't pause at lesson 1 and stop until you can continue. Right? Yeah. So this approach is based on a lot of research, academic research into learning theory. And one guy in particular, David Perkins from Harvard, has this really great analogy. He's a researcher into learning theory. He describes this approach of the whole game, which is basically if you're teaching a kid to play soccer, you don't, first of all teach them about, how the friction between a ball and grass works, and then teach them how to sew a soccer ball with their bare hands, and then teach them the mathematics of parabolas when you kick something in the air. No, you say, here's a ball. Let's watch some people playing soccer. Okay, now we'll play soccer. And then you gradually over the following years learn more and more so that you can get better and better at it. So this is kind of what we're trying to get you to do, is to play soccer, which in our case is to type code and look at the inputs and look at the outputs. Okay, so let's dig into our first notebook, which is called Lesson 2 Download. And what we're going to do is we're going to see how to create your own classifier with your own images. So it's going to be a lot like last week's pet detector, but it'll detect whatever you like. So it'll be like those some of those examples we just saw. How would you create your own Panama bus detector from scratch? So this is inspired, the approach is inspired by Adrian Rosebrock, who has a terrific website called PyImageSearch, and he has this nice explanation of how to create a data set using Google Images. So that was definitely an inspiration for some of the techniques we use here. So thank you to Adrian. And you should definitely check out his site. It's full of lots of good resources. So, so here we are. So we are going to try to create a teddy bear detector. Thanks. We're going to try and make a teddy bear detector, and we're going to try and separate teddy bears from black bears from grizzly bears. This is very important. I have a 3-year-old daughter, and she needs to know what she's dealing with. In our house, you would be surprised at the number of monsters, lions, and other terrifying threats that are around, particularly around Halloween. And so we always need to be on the lookout to make sure that the thing we're about to cuddle is in fact a genuine teddy bear. Okay, so let's deal with that situation as best as we can. So our starting point is to find some pictures of teddy bears so we can learn what they look like. So I go to images.google.com and I type in teddy bear, and I just scroll through until I kind of find a goodly bunch of them. And it's like, okay, that looks like plenty of teddy bears to me. So then I'll go back to here. So you can see it says search and scroll. Go to Google Images and search. And the next thing we need to do is to get a list of all of the URLs there. And so to do that, you back in your Google Images, you hit Control-Shift-J or Command-Option-J, and you paste this into the window that appears. So I've got Windows, so I go Control-Shift-J, paste in that code. So this is a JavaScript console. For those of you who haven't done any JavaScript before, I hit Enter, and it downloads my file for me. So I would call this teddies.txt and press Save. Okay, so I now have a file of teddies, or URLs of teddies. So then I would repeat that process for black bears and for brown bears, since that's a classifier I would want, and I'd put each one in a file with an appropriate name. So that's step 1. So step 2 is we now need to download those URLs to our server. Because remember, when we're using Jupyter Notebook, it's not running on our computer, it's running on SageMaker or Cressel or Google Cloud or whatever. So To do that, we start running some Jupyter cells. So let's grab the FastAI library, and let's start with black bears. I've already got my black bears URL. So I'll click on this cell for black bears, and I'll run it. See here how I've got 3 different cells with doing the same thing but different information. This is one way I like to work with Jupyter Notebook. It's something that a lot of kind of people with a more strict scientific background are horrified by. This is not reproducible research. I actually click here and I run this cell to create a folder called black and a file called URLs black for my black bears. I skip the next 2 cells and then I run this cell to create that folder. Okay. And then I go down to the next section and I run the next cell, which is download images for black bears. Right? So that's just going to download my black bears to that folder. And then I'll go back and I'll click on teddies and I'll run that cell and then scroll back down and I'll run this cell. And so that way I'm just going backwards and forwards to download each of the classes that I want. Very manual, but for me, I'm very iterative, I'm very experimental. That works well for me. If you're better at kind of planning ahead than I am, you can, write a proper loop or whatever and do it that way. But when you see my notebooks and see things where there's these kind of like configuration cells doing the same thing in different places, this is a strong sign that I didn't run this in order, right? I clicked one place, went to another, ran that, went back, went back, went back. And for me, I'm an experimentalist. I really like to experiment in my notebook. I treat it like a lab journal. I try things out and I see what happens. And so this is how my notebooks end up looking. It's a really controversial topic. Like for a lot of people, they feel this is like wrong, that you should only ever run things top to bottom. Everything you should do should be reproducible. For me, I don't think that's the best way of using human creativity. I think human creativity is best inspired by trying things out, seeing what happens, and fiddling around. So you can see how you go, see what works for you. So that will download the images to your server. It's going to use multiple processors to do so, and one problem there is if there's something goes wrong, it's a bit hard to see what went wrong. So you can see in the next section there's a commented out section that says max workers equals 0, and that'll do it without spinning up a bunch of processes and will tell you the errors better. So if things aren't downloading, try using the second version. Okay, so it takes, so I grabbed a small number of each, and then the next thing that I found I needed to do was to remove the images that aren't actually images at all. And this happens all the time. There's always a few images in every batch that are corrupted for whatever reason. Google image tried to told us that this URL had an image, but actually it doesn't anymore. So we've got this thing in the library called verify images, which will check all of the images in a path, and will tell you if there's a problem. If you say delete equals true, it will actually delete it for you. Okay, so that's a really nice, easy way to end up with a clean data set. So at this point, I now have a bears folder containing a grizzly folder and a teddies folder and a black folder. In other words, I have the basic structure we need to create an image data bunch to start doing some deep learning. So let's go ahead and do that. Now, very often when you download a data set from like Kaggle or from some academic data set, there will often be a folder called train and a folder called valid and a folder called test, right, containing the different data sets. In this case, we don't have a separate validation set because we just grab these images from Google search, right? But you still need a validation set, otherwise you don't know how well your model is going. And we'll talk more about this in a moment. So whenever you create a data bunch, if you don't have a separate training and validation set, then you can just say, okay, well the training set is in the current folder, because by default it looks in a folder called train, and I want you to set aside 20% of the data, please. So this is going to create a validation set for you automatically and randomly. You'll see that whenever I create a validation set randomly, I always set my random seed to something fixed beforehand. This means that every time I run this code, I'll get the same validation set. So in general, I'm not a fan of making my machine learning experiments reproducible, i.e. ensuring I get exactly the same result every time. The randomness is, to me, really important. A really important part of finding out, is your solution stable? You know, is it going to work like each time you run it? But what is important is that you always have the same validation set, right? Otherwise, when you're trying to decide, has this hyperparameter change improved my model, but you've got a different set of data you're testing it on, then you don't know, maybe that set of data just happens to be a bit easier, right? So that's why I always set the random seed here. So we've now got, let's run that cell. So we've now got a data bunch. And so you can look inside at the data.classes, and you'll see these are the folders that we created. So it knows that the classes, or, you know, so by classes we mean all the possible labels, black bear, grizzly bear, or teddy bear. We can run show batch, and we can take a little look. And it tells us straight away that some of these are going to be a little bit tricky. So this is not a photo, for instance. Some of them kind of cropped funny. Some of them might be tricky, like if you ended up with a black bear standing on top of a grizzly bear, that might be tough. Anyway, so you can kind of double check here, data.classes, there they are. Remember, C is the attribute which the classifiers tells us how many possible labels there are. We'll learn about some other more specific meanings of C later. We can see how many things are in our training set. We can see how many things are in our validation set. So we've got 473 training set, 141 validation set. So at that point we can go ahead. You'll see all these commands are identical to the PET classifier from last week. We can create our CNN, our convolutional neural network, using that data. I tend to default to using a ResNet 34. And let's print out the error rate each time and run fit one cycle 4 times and see how we go. And we have a 2% error rate. So that's pretty good. I personally aren't, I mean, sometimes it's easy for me to recognize a black bear from a grizzly bear, but sometimes it's a bit tricky. This one seems to be doing pretty well. Okay, so after I kind of make some progress with my model and things are looking good, I always like to save where I'm up to save me the 54 seconds of going back and doing it again. And as per usual, we unfreeze the rest of our model. We're going to be learning more about what that means during the course. And then we run the learning rate finder and plot it. It tells you exactly what to type. And we take a look. Now, we're going to be learning about learning rates today, actually. But for now, here's what you need to know. On the learning rate finder, what you're looking for is the strongest downward slope that's kind of sticking around for quite a while, right? So this one here looks more like a bump, but this looks like an actual downward slope to me. So it's kind of like, it's something you're going to have to practice with and get a feel for, like which bit works. So like if you're not sure, is it this bit or this bit, try both learning rates and see which one works better. Okay, but I've been doing this for a while, and I'm pretty sure this looks like where it's really learning properly. So I would pick something, okay, here it's not so steep, so I would probably pick something back here for my learning rate. So you can see I picked 3e neg 5, so, you know, somewhere around here. That sounds pretty good. So that's for my bottom learning rate. For my top learning rate, I normally pick, you know, 1e neg 4 or 3e neg 4. It's kind of like I don't really think about it too much. That's a rule of thumb. It always works pretty well. One of the things you'll realize is that most of these parameters don't actually matter that much in detail. If you just copy the numbers that I use each time, the vast majority of the time it'll just work fine. And we'll see places where it doesn't today. Okay, so we've got a 1.4% error rate after doing another couple of epochs. So that's looking great. So we've downloaded some images from Google Image, search, created a classifier. We've got a 1.4% error rate. Let's save it. And then as per usual, we can use the classification interpretation class to have a look at what's going on. And in this case, we made one mistake. There was one black bear classified as a grizzly bear. So that's a really good step. We've come a long way. But possibly you could do even better if your data set was less noisy. Like maybe Google image search didn't give you exactly the right images all the time. So how do we fix that? And so we want to clean it up. And so combining a human expert with a computer learner is a really good idea. Almost not nobody, but very, very few people publish on this. Very, very few people teach this. But to me, it's like the most useful skill, particularly for you. You know, most of the people watching this are domain experts, not computer science experts. And so this is where you can use your knowledge of, you know, point mutations in genomics or Panamanian buses or whatever. So let's see how that would work. What I'm going to do is, do you remember the plot top losses from last time where we saw the images which it was like either the most wrong about or the least confident about? We're going to look at those and decide which of those are noisy. Like if you think about it, it's very unlikely that if there is some mislabeled data, that it's going to be predicted correctly and with high confidence. That's really unlikely to happen. So we're going to focus on the ones which the model is saying either it's not confident of or it was confident of and it was wrong about. They are the things which might be mislabeled. Big shout out to the San Francisco FastAI study group who created this new widget this week called the file deleter. That's Zach and Jason and Francisco built this thing where we basically can take the top losses from that interpretation object we just created, right? And then what we're going to do is we're going to say, okay, that returns top losses. There's not just plot top losses, but there's also just top losses. And top losses returns two things, the losses of the things that were the worst, and the indexes into the data set of the things that were the worst. And if you don't pass anything at all, it's going to actually return the entire data set, but sorted. So the first things will be the highest losses. As we'll learn during the course, or we'll keep seeing during the course, every data set in FastAI has an X and a Y. And the X contains the things that are used to, in this case, get the images. So this is the image file names, and the Ys will be the labels. So if we grab the indexes and pass them into the data set X, this is going to give us the file names of the data set ordered by which ones had the highest loss. So which ones it was either confident and wrong about or not confident about. And so we can pass that to this new widget that they've created called the file deleter widget. So just to clarify, this top loss paths contains all of the file names in our data set. When I say in our data set, this particular one is in our validation data set. So what this is going to do is it's going to clean up mislabeled images or images that shouldn't be there. And we're going to remove them from a validation set so that our metrics will be more correct. You then need to rerun these two steps, replacing valid DS with train DS, to clean up your training set to get the noise out of that as well. So it's a good practice to do both. We'll talk about test sets later as well. If you also have a test set, you would then repeat the same thing. So we run file deleter, passing in that sorted list of paths. And so what pops up is basically the same thing as plot top losses. So in other words, these are the ones which is either wrong about or least confident about. And so not surprisingly, this one here does not appear to be a teddy bear or a black bear or a brown bear, right? So this shouldn't be in our data set. So what I do is I whack on the delete button. Okay, and all the rest do look indeed like bears, and then so I can click confirm, and it'll bring up another 5. What's that? That's not a bear, is it? Does anybody know what that is? I'm going to say that's not a bear. Delete, confirm. Oh, not bear. Well, that's a teddy bear. I'll leave that. That's not really. I'll get rid of that one. Confirm. Okay, so what I tend to do when I do this is I'll keep going confirm until I get to a couple of screenfuls of things that all look okay. And that suggests to me that I've kind of got past the worst bits of the data. Okay, and that's it. And so now you can go back, once you do it for the training set as well, and retrain your model. So I'll just note here that what our San Francisco study group did here was that they actually built a little app inside Jupyter Notebook, which you might not have realized is possible. But not only is it possible, it's actually surprisingly straightforward. And just like everything else, you can hit double question mark to find out their secrets. So here is the source code, okay? And really, if you've done any GUI programming before, it'll look incredibly normal. You know, there's basically callbacks for what happens when you click on a button, where you just do standard Python things, and to actually render it, you just use widgets, and you can lay it out using standard boxes and whatever. So this idea of creating applications inside notebooks is like, it's really underused, but it's super neat because it lets you create tools for your fellow practitioners, for your fellow experimenters, right? And you could definitely envisage taking this a lot further. In fact, by the time you're watching this on the MOOC, you'll probably find that there's a whole lot more buttons here because we've already got a long list of to-dos that we're going to add to this particular thing. So that's it. So I think like I'd love for you to have a think about, now that you know it's possible to write applications in your notebook, what are you going to write? And if you Google for IPy widgets, you can learn about the little GUI framework to find out what kind of widgets you can create and what they look like and how they work, and so forth. And you'll find it's actually a pretty, complete GUI programming environment that you can play with, and this will all work nicely with your models and so forth. It's not a great way to productionize an application because it is sitting inside a notebook. This is really for things which are going to help other practitioners, other experimentalists, and so forth. For productionizing things, you need to actually build a production web app, which we'll look at next. Okay, so after you have cleaned up your noisy images, you can then retrain your model, and hopefully you'll find it's a little bit more accurate. One thing you might be interested to discover when you do this is it actually doesn't matter most of the time very much. On the whole, these models are pretty good at dealing with moderate amounts of noisy data. The problem would occur is if your data was not randomly noisy, but biased noisy. So I guess the main thing I'm saying is if you go through this process of cleaning up your data and then you rerun your model and find it's like 0.001% better, that's normal. Okay, it's fine, but it's still a good idea just to make sure that you don't have too much noise in your data in case it is biased. So at this point, we're ready to put our model in production. And this is where I hear a lot of people ask me about, which mega Google, Facebook, highly distributed serving system they should use, and how do they use 1,000 GPUs at the same time, and whatever else. For the vast majority of things that you all do, you will want to actually run in production on a CPU, not a GPU. Why is that? Because a GPU is good at doing lots of things at the same time. But unless you have a very busy website, it's pretty unlikely that you're going to have 64 images to classify at the same time to put into a batch into a GPU. And if you did, you've got to deal with all that queuing and running it all together. All of your users have to wait until that batch has got filled up and run. It's a whole lot of hassle, right? And then if you want to scale that, there's another whole lot of hassle. It's much easier if you just grab one thing, throw it at a CPU to get it done, and it comes back again. So yes, it's going to take, maybe 10 or 20 times longer, right? So maybe it'll take 0.2 seconds rather than 0.01 seconds. That's about the kind of times we're talking about. But it's so easy to scale, right? You can chuck it on any standard serving infrastructure. It's going to be cheap as hell. You can horizontally scale it really easily, right? So most people I know who are running apps that aren't kind of at Google scale based on deep learning are using CPUs. And the term we use is inference, right? So when you're not training a model, but you've got a trained model and you're getting it to predict things, we call that inference. So that's why we say here you probably want to use CPU for inference. So at inference time, you've got your pre-trained model, you've saved those weights, and how are you going to use them to create something like Simon Willison's Cougar detector? Well, first thing you're going to need to know is what were the classes that you trained with, right? You need to know not just what are they, but what was the order, okay? So you will actually need to like serialize that or just type them in or in some way make sure you've got exactly the same classes that you trained with. If you don't have a GPU on your server, it will use the CPU automatically. If you want to test, if you have a GPU machine and you want to test using a CPU, you can just uncomment this line, and that tells FastAI that you want to use CPU by passing it back to PyTorch. So here's an example. We don't have a cougar detector. We have a teddy bear detector, and my daughter Claire is about to decide whether to cuddle this friend. Okay, so what she does is she takes Daddy's deep learning model and she gets a picture of this, and here is the picture that she's uploaded to the web app. Okay, and here is a picture of the potentially cuddlesome object. And so we're going to store that in a variable called image. So open image is how you open an image in FastAI, funnily enough. Here is that list of classes that we saved earlier. And so as per usual, we created a data bunch. But this time we're not going to create a data bunch from a folder full of images. We're going to create a special kind of data bunch, which is one that's going to grab one single image at a time. So we're not actually passing it any data. The only reason we pass it a path is so that it knows where to load our model from, right? That's just the path, that's the folder that the model's going to be in. But what we do need to do is that we need to pass it the same information that we trained with, so the same transforms, the same size, the same normalization. This is all stuff we'll learn more about, but just make sure it's the same stuff that you used before. And so now you've got a data bunch that actually doesn't have any data in it at all. It's just something that knows how to transform a new image in the same way that you trained with, so that you can now do inference. So you can now create a CNN with this kind of fake data bunch, and again, you would use exactly the same model that you trained with. You can now load in those saved weights, okay? And so this is the stuff that you would do just once when your web app's starting up, okay? And it takes, 0.1 of a second to run this code. And then you just go learn.predict image. And it's lucky we did that because it is not a teddy bear. This is actually a black bear. So thankfully, due to this excellent deep learning model, my daughter will avoid having a very embarrassing black bear cuddle incident. So what does this look like in production? Well, I took Simon Willison's code and shamelessly stole it, made it probably a little bit worse, but basically it's going to look something like this. So Simon used a really cool web app toolkit called Starlet. If you've ever used Flask, this will look extremely similar, but it's kind of a more modern approach. And by modern, what I really mean is that you can use a wait. Which basically means that you can wait for something that takes a while, such as grabbing some data, without using up a process. So for things like I want to get a prediction, or I want to load up some data, or whatever, it's really great to be able to use this modern Python 3 asynchronous stuff. So Starlet would come highly recommended for creating your web app. And so, yeah, you just create a route as per usual in a web app. And in that, you say this is async to ensure that it doesn't steal a process while it's waiting for things. You open your image, you call .predict, and you return that response. And then you can use a whatever JavaScript client or whatever to show it. And that's it. That's basically the main contents of your web app. So give it a go, right? You know, this week, even if you've never created a web application before, there's a lot of you know, nice little tutorials online and kind of starter code. You know, if in doubt, why don't you try Starlet? There's a free hosting that you can use. There's one called Python Anywhere, for example. The one that Simon's used, we'll mention that on the forum. It's something you can basically package it up as a Docker thing and shoot it off, and it'll serve it up for you. So it doesn't even need to cost you any money. And so all these classifiers that you're creating, you can turn them into web applications. So I'll be really interested to see what you're able to make of that. That'll be really fun. Okay, so let's take a break. We'll come back at 7:35. See you then. Okay, so let's move on. So I mentioned that most of the time, the kind of rules of thumb I've shown you will probably work. And if you look at the Share Your Work thread, you'll find most of the time people are posting things saying, I downloaded these images, I tried this thing, it worked much better than I expected, well, that's cool. And then like 1 out of 20 says like, I had a problem. So let's have a talk about what happens when you have a problem. And this is where we're starting to start getting into a little bit of theory, because in order to understand why we have these problems and how we fix them, it really helps to know a little bit about what's going on. So first of all, let's look at examples of some problems. The problems basically will be either your learning rate is too high or low, or your number of epochs is too high or low. So we're going to learn about what those mean and why they matter. But first of all, because we're experimentalists, let's try them. All right? So let's go with our teddy bear detector, and let's make our learning rate really high. The default learning rate is 0.003. It works most of the time. So what if we try a learning rate of 0.5? That's huge. What happens? Our validation loss gets pretty damn high. Right? Remember, this is normally something that's underneath 1. Right? So if you see your validation loss do that, right, before we even learn what validation loss is, just know this. If it does that, your learning rate's too high. That's all you need to know. Okay? Make it lower. Doesn't matter how many epochs you do. And if this happens, there's no way to undo this. You have to go back and create your neural net again and fit from scratch with a lower learning rate. So that's learning rate too high. Learning rate too low. What if we use a learning rate not of 0.003, but 1e-5, so 0.00001, right? So this is just, I've just copied and pasted what happened when we trained before with our default error, right, with our default learning rate, and within 1 epoch we were down to a 2 or 3% error rate. With this really low learning rate, our error rate does get better, but very, very slowly, right? And you can plot it. If you go learn, so learn.recorder is an object which is going to keep track of lots of things happening while you train. You can call plot losses to plot out the validation and training loss, and you can just see them just like gradually going down so slow. Right? So if you see that happening, then you have a learning rate which is too small. Okay, so bump it up by 10 or bump it up by 100 and try again. The other thing you'll see if your learning rate is too small is that your training loss will be higher than your validation loss. You never want a model where your training loss is higher than your validation loss. That always means you haven't fitted enough, which means either your learning rate is too low or your number of epochs is too low. So if you have a model like that, train it some more or train it with a higher learning rate. Okay? Too few epochs. So what if we train for just 1 epoch? our error rate certainly is better than random. It's 5%. But look at this. The difference between training loss and validation loss. The training loss is much higher than the validation loss. So too few epochs and too lower learning rate look very similar, right? And so you can just try running more epochs. And if it's taking forever, you can try a higher learning rate. Or if you try a higher learning rate and the loss goes off to 100,000 million, then put it back to where it was and try a few more epochs. That's the balance, right? That's basically all you care about 99% of the time. And this is only the 1 in 20 times that the defaults don't work for you. Okay, too many epochs, we're going to be talking more about this, create something called overfitting. If you train for too long, as we're going to learn about, it will learn to recognize your particular teddy bears, but not teddy bears in general. Here's the thing. Despite what you may have heard, it's very hard to overfit with deep learning. So we were trying today to show you an example of overfitting, and I turned off everything. And we're going to learn all about these terms soon. I turned off all the data augmentation. I turned off dropout. I turned off weight decay. I tried to make it overfit as much as I can. I trained it on a small-ish learning rate. I trained it for a really long time. And like, maybe I started to get it to overfit, maybe. So the only thing that tells you that you're overfitting is that the error rate improves for a while and then starts getting worse again. You will see a lot of people, even people that claim to understand machine learning, tell you that if your training loss is lower than your validation loss, then you are overfitting. As you will learn today in more detail and during the rest of the course, that is absolutely not true. Any model that is trained correctly will always have train loss lower than validation loss. That is not a sign of overfitting. That is not a sign you've done something wrong. That is a sign you have done something right. Okay. The sign that you are overfitting is that your error starts getting worse. Because that's what you care about, right? You want your model to have a low error. So as long as you're training and your model error is improving, you are not overfitting. How could you be? Okay? So there's basically the they're the main 4 things that can go wrong. There are some other details that we will learn about during the rest of this course. But honestly, if you stopped listening now, please don't, that would be embarrassing. And you just like, okay, I'm going to go and download images. I'm going to create CNNs with ResNet 34 or ResNet 50. I'm going to make sure that my learning rate and number of epochs is okay. And then I'm going to chuck them up in a Starlet web API. Most of the time you're done, okay? At least for computer vision. Hopefully you'll stick around because you want to learn about NLP and collaborative filtering and tabular data and segmentation and stuff like that as well. Let's now understand what's actually going on. What does it mean, loss mean? What does an epoch mean? What does learning rate mean? Because for you to really understand these ideas, you need to know what's going on. And so we're going to go all the way to the other side. Rather than creating a state-of-the-art cougar detector, we're going to go back and create the simplest possible linear model. Okay? So we're going to actually start seeing a little bit of math. Okay, but don't be turned off. It's okay, right? We're going to do a little bit of math, but it's going to be totally fine even if math's not your thing. Because the first thing we're going to realize is that when we see a picture, like this number 8, it's actually just a bunch of numbers. It's a matrix of numbers. For this grayscale one, it's a matrix of numbers. If it was a color image, it would be have a third dimension. So when you add an extra dimension, we call it a tensor. Rather than a matrix, it would be a 3D tensor of numbers, red, green, and blue. So when we created that teddy bear detector, what we actually did was we created a mathematical function that took the numbers from the images of the teddy bears, and the mathematical function converted those numbers into, in our case, 3 numbers. a number for the probability that it's a teddy, a probability that it's a grizzly, and a probability that it's a black bear. In this case, there's some hypothetical function that's taking the pixels representing a handwritten digit and returning 10 numbers, the probability for each possible outcome, the numbers from 0 to 9. And so what you'll often see in our code and other deep learning code is that you'll find this a bunch of probabilities, and then you'll find something called max or argmax attached to it, a function called. And so what that function is doing is it's saying, find the highest number, so the highest probability, and tell me what the index is. So np.argmax or torch.argmax of this array would return this number here. Okay, we return index 8. Does that make sense? In fact, let's try it. So we know that the function to predict something is called learn.predict. Okay, so we can chuck 2 question marks before it or after it to get the source code. And here it is, right? Pred equals res result dot argmax. And then what is the class? Well, you just pass that into the classes array. So like you should find that the source code in the FastAI library can both kind of strengthen your understanding of the concepts and make sure that you know what's going on and really help you here. You got a question? Come on over.
All right, so can we have a definition of the error rate being discussed and how it is calculated? I assume it's cross-validation error.
Sure. So one way to answer the question of how is error rate calculated would be to type error rate question mark and look at the source code, and it is 1 minus accuracy. Fair enough. And so then a question might be, what is accuracy? Accuracy question mark. It is argmax. So we now know that means find out which particular thing it is, and then look at how often that equals the target. So in other words, the actual value, and take the mean. So that's basically what it is. And so then the question is, okay, well, what is that being applied to? Always in FastAI, metrics, so these things that we pass in, we call them metrics, are always going to be applied to the validation set. Okay? So anytime you put a metric here, it'll be applied to the validation set because that's your best practice, right? That's what you always want to do, is make sure that you're checking your performance on data that your model hasn't seen. And we'll be learning more about the validation set shortly. Remember, you can also type doc. If the source code is not what you want, which it might well not be, you actually want the documentation. That will both give you a summary of the types in and out of the function and a link to the full documentation where you can find out all about how metrics work and what other metrics there are and so forth. And generally speaking, you'll also find links to more information where, for example, you will find complete runs through and sample code and so forth showing you how to use all these things. So don't forget that the doc function is your friend. Okay, and also in the documentation, both in the doc function and in the documentation, you will see a source link. This is like question mark, but what the source link does is it takes you into the exact line of code in GitHub, so you can see exactly how that's implemented and what else is around it. So lots of good stuff there.
Why were you using 3s for your learning rates earlier with 3e neg 5 and 3e neg 4? We found that 3e neg 3 is just a really good default learning rate. It works most of the time for your initial fine-tuning before you unfreeze. And then I tend to kind of just multiply from there. So I generally find then that the next stage I will pick 10 times lower than that for the second part of the slice,
and whatever the LR finder found for the first part of the slice. The second part of the slice doesn't come from the LR finder. It's just a rule of thumb, which is like 10 times less than your first part, which defaults to 3e neg 3. And then the first part of the slice is what comes out of the LR finder. And we'll be learning a lot more about these learning rate details both today and in the coming lessons. But yeah, for now, all you need to remember is that in your basic approach looked like this. It was learn